紧接着要进入的是我们今天的第一个议程 ，Cutting Edge Hadoop Technology and the Trend。我们邀请到趋势科技资深架构师 HBase PMC 提教人 Andrew Purtell 为我们主讲。Let's welcome Andrew Purtell with one Mr. Clap.
Morning. So a word before I start my presentation. I have a lot of material to cover, and there's a lot of material on the slides, including URLs. So not expected that you all absorb it while I page through it. The slides will be made available after my presentation for your research at your leisure. And I think also, since Mr. Chang made such an excellent introduction, I can skip through my first few slides, which is always a good thing. It leaves more time for questions at the end. So with that, let me get started. Okay, so first, introduction, who am I? Well, I'm an engineer with about 15 years experience in systems engineering. I spent a number of years in a research setting as well as commercial settings. For Trend Micro, I've been a software architect in the Hadoop space. I've been involved since 2008. My first experience with Hadoop and HBase was Hadoop version 17 and HBase version 0.1. And I was reflecting on that the other day, how far these open source software systems have come in that time. And if you tried those versions today, you would be shocked at how primitive they are compared to what we have today. It's been an interesting journey. And since 2009, I've been a committer and a project management committee member for the Apache HBase project. So I've had a lot of time out in the Apache open source community, and it's been very fun and rewarding. And my current role at Trend is the manager of Trend's Hadoop group. We package the Apache Hadoop artifacts for our internal stakeholders, and we act as a go-between between their needs and community-based development. So I wanted to introduce a little bit about Hadoop and big data. Why are we here talking about Hadoop in the first place? It seems like the case has already been made. Essentially, organizations increasingly have a data problem. I would argue that the currency of this century is information. So if you can master your information flow, you can master your cash flow. And in fact, it's necessary to master your information flow in order to be successful. But speaking about big data, why are we now talking about data that's big? It's, as we're moving through rapid evolution of business models from the internet into cloud, into mobile space, into social media, the number of participants in those ecosystems is increasing a lot. And the network effects of all of the interactions between those entities, be they people, be they machines, is increasing as well, along three dimensions, not just in terms of size, but also in terms of how quickly the data types or the representations evolve, also how fast this information is coming. So it's commonly referred to as the 3V model, right? Volume, variety, and velocity. Any of these things can be big data. It just doesn't have to be big in terms of size. And this is being driven by smartphone adoption and social media, the Internet of Things, the rapid rise in popularity of cloud computing, and the demonstrative improvement in business outcomes for companies that adopt these technologies. Now let's try to quantify what might be the upper bound of the scale of big data. If you think of the number of humans or potential information sources on the planet currently clock in at about 7.039 billion. And now not every human has a device and it can participate in the information economy, but you know what, pretty close, actually. The percentage of humans who own a mobile phone now is somewhere in north of 80%, and that's really, really significant. And out of the 5 or so billion mobile phones in the world, about 1.8 are estimated to be 1.08 billion are estimated to be smartphones. But furthermore, going forward, we have the Internet of Things. And I don't want to belabor the point, but just say that in the coming years, as more automated devices come online and are added into the cloud, we may be looking at wanting to keep state on 50 to 100 trillion, 50 to 100 trillion objects collectively know something about that. And that's just a massive amount of information. So with that amount of information, how does one manage it? And how does one manage it in an economical way? And this is why we're sitting here talking today about Hadoop. Because Hadoop has become a de facto commodity platform for big data. You can combine commodity, and we'll use those terms maybe a little bit loosely, but commodity hardware. So your hardware is affordable, and the software is eminently affordable, being free. So you can manage the cost of deploying a lot of hardware and software to deal with a lot of data. And so Hadoop maybe hasn't been the first system to meet this criteria, but it came along at just the right moment to take off. So that's why we're talking about Hadoop today. And so why is Hadoop widely adopted for handling big data? Because at high scale, commodity is the only route to affordability, mainly. And Hadoop has been designed to solve a particular use case that can, or Hadoop encodes a particular computation model that's widely applicable to many different types of data and problems. And although I'm going to get into some of the limitations of Hadoop in a little bit in my talk, generally speaking, Hadoop is self-healing and therefore can run large-scale jobs, high-performance jobs with fault tolerance, simple enough so that many people can use. And there's a large and growing ecosystem of tools, each of them handling a different slices of the volume, velocity, or variety space. And also, I'd argue that Hadoop has become the center of a new data warehousing ecosystem. Okay, so that's Hadoop. We have a big data problem. Hadoop is a commodity solution for big data, but Hadoop is definitely not perfect. And one thing that I like about my time at Trend Micro is I work with a lot of engineers who are very passionate about open source and would like to contribute and maybe don't know where they can contribute or where they can best direct their efforts in the Hadoop space. Like, we want to contribute to Hadoop. How do we do that? So the rest of my talk is dedicated towards talking about the cutting edge of Hadoop, and you will find the cutting edge of Hadoop where Hadoop pain points are. And if you wanted to focus your contributions or potential contributions in the Hadoop space at these problems, this is where you would make the maximum impact. So where is the Hadoop cutting edge? So we've seen widespread adoption of Hadoop, and new users have tested its limits, and so some shortcomings have been apparent. And they basically boil down to the following. So where high availability is crucial, when the map-reduced computational model is a poor fit for what you're trying to do, when decisions must be made quickly, because as we know, Hadoop is a batch processing system, when a SQL-like interface presented by Hive, for example, might set the wrong user expectations, this is more of a product side issue than a user side issue. Issues presented by the JVM, because as we know, Hadoop is based on Java, and it brings along Java's benefits and shortcomings. And issues presented by the increasing density and affordability of solid state. Basically, all of the Hadoop stack was designed for spinning media, not solid state. So there's a lot of challenges there. And when GPU offload is desired, because it's becoming very hot. Well, there's a lot of interest in scientific computing on GPU offload. And we haven't really thought about how to do that in the Hadoop space yet. So we find the cutting edge and trends in Hadoop where these problems lie. So let me talk a little bit about where high availability is crucial. So the problem is basically the design of the Hadoop distributed file system, at least the Hadoop distributed file system version 1. There is a single name node. This was an engineering decision that worked very well for a long period of time. It's simplified and solved a lot of engineering challenges to have just one device keep all of the file system metadata state in memory. Problem is, if it goes, everything goes. It's a house of cards. The entire house of cards collapses. So new in Hadoop 2, we find the cutting edge of HDFS, the ability to deploy active and standby name nodes with manual or automatic failover. Now, this is what's currently shipping in Hadoop. There's a new failover control component, and like I said, the name node, now you run 2 name nodes, an active and standby mode, and there's tooling to automate failover and fencing and the promotion of the backup into the primary and that sort of thing. But if you look in the beginning, if you look in the middle, I'm sorry, of this architecture, this is Hadoop 2.0.0 alpha. Now the high availability solution there is, well, everybody shares state except for the edit log. Now we still need to get the edit log from the primary to the backup. How do we do that? Well, we'll use an NFS filer. Except, to my mind, NFS filer just means you move the single point of failure from the name node now to a filer. So again, if we want to talk about cutting edge in Hadoop, now we're doing currently, right now, further improvements in the development of the high availability solution for HDFS, with the introduction of the quorum journal node as one option, or the bookkeeper journal node as another option. And I have links up on the slides to JIRAs and the tickets tracking these issues in Apache open source. And this is not quite done yet. These are both a work in progress, but they're almost to be delivered. And so if you were looking to be on the cutting edge of HDFS and have a truly highly available HDFS, then I would personally encourage you to pick up the quorum journal node solution and try to integrate that into your platform. You'll have zero single point of failure HDFS, perhaps for the first time. And this is what we're doing in Trend Micro. Also, HDFS version 2 in Hadoop 2 offers now the capability to federate your HDFS, so split the namespace. And this is an interesting additional engineering option for you if you have multiple applications running against Hadoop. Now you don't necessarily have to worry about the single point. I mean, currently in Hadoop 1, all of your applications run on the singleton name node, right? So if this name node dies, then all of your applications are dead. So now we've moved to Hadoop 2, say, and we have a highly available HDFS name node, but you still have all of your applications talking to that one name node, right? So you still have a global failure domain. But with HDFS federation, it offers the possibility to partition your HDFS service while still maintaining the economy of scale of a single shared pool of data nodes, but yet have reserved pieces or divide pieces of the namespace and dedicate name nodes or HA name node pairs to each application. So if even with an HA name node you still have a failure, it only takes down one application instead of all of your applications. And I don't think anybody has really done a deployment like this yet, so a deployment that tried to leverage this for that reason would be cutting edge. Getting back to the single points of failure in Hadoop 1, we have also the singleton job tracker. It's the same issue. There's only one of them. It's convenient for design, but if it dies, then there's no service for MapReduce. Well, again, in Hadoop 2, now we have Yarn. Yarn stands for yet another resource negotiator, I think. For our purposes of discussion here, I would like to point out that Yarn has a truly highly available architecture. So now there's a generic resource broker. It is a highly available service, and each job, each MapReduce job is a cluster within a cluster. So getting back to what we were talking about before about partitioning up failure domains, each job is now its own failure domain. You don't have a global failure domain centered on the name node. Sorry, on the job tracker. Okay, moving on to when MapReduce might be a poor fit. So I think the canonical example is graph algorithms, because a lot of graph algorithms are iterative in nature. And the problem fundamentally with MapReduce is it's a powerful, high throughput batch computation. But for iteration, that means you have to run more than one job until your algorithm converges. And since MapReduce doesn't maintain any state between jobs, you have to save all of the state of your previous iteration and then load it all back in for your next iteration, which is horribly inefficient where when you really want to do is for an iterative computation, keep all of that state in memory through each iteration. So you don't have to, so you can skip that load state. And also inside the MapReduce job itself, there's a shuffle phase which you may not need. So you're taking an overhead at each iteration of shuffles. So we can do better. And getting back to Yarn, what Yarn has done is generalize Hadoop 2 to admit new computational models alongside MapReduce jobs. Basically, MapReduce becomes a library. And now you can deploy other things like Apache Giraffe or OpenMPI or Spark or experimental changes to the MapReduce model optimizing for iteration, for example, like Hadoop. run it alongside your production MapReduce jobs, and they don't interfere with each other. So it opens the Hadoop cluster to be so much more than just MapReduce. And this is definitely an area of cutting edge. What new computation models can you run in Yarn? So you have a single tool chain to manage all of these different computations, but the space of what kind of computational model you can run on your Hadoop cluster is wide open for you to fill with something. And so getting back to Hadoop, just as a specific example, this is a academic research project which looks at how to optimize iterative jobs in MapReduce, and they make some changes to the MapReduce framework. That would kill you if you try to do that in Hadoop 1, because now you've made a global change across all of your MapReduce jobs with some experimental thing that may be a problem. But with Hadoop 2, with Yarn, you can leave your production untouched and do something like Hadoop and look, if you look at the graph at the bottom of this slide, Hadoop essentially makes the linear cost of iterations sublinear, which can be a huge improvement in the runtime. So pictorially, here's a representation of MapReduce running as essentially its own cluster within a cluster, and something like Giraffe running as its own cluster within a cluster. And their resources and activities are isolated from each other by Yarn. And I would also like to direct your attention to SAP Labs platform as a service on Yarn prototype, because this is just an interesting idea, and they're not going to productize this, I don't think. But Yarn actually, Hadoop grows up and becomes a true grid scheduling system. It's not MapReduce anymore, it can be anything. Containers they simply reserve and allocate CPU and memory and disk resources independently, right? Containers can execute any kind of program. Well, potentially, it could be the underpinning of a platform as a service platform. So it's not just Hadoop now, it's almost Hadoop stack, cloud stack, Hadoop stack. It's an interesting idea. I'd like to direct your attention specifically to Apache Giraffe for graph algorithms. Giraffe is a promising new project in Apache land. It brings iterative in-memory graph computation to the Hadoop platform. And it uses, what I think is interesting is it's in-memory graph computation is a totally different way of doing graph computation than MapReduce. However, they've spent some time to use Hadoop-like concepts in the API for familiarity. If you've done Hadoop programming before, you'll find things like writables and combiners and input and output formats. So the landscape is familiar for you to start working with Giraffe. And from an operational point of view, Giraffe runs as mappers. So all of the standard tools for managing your Hadoop cluster work equally well with Giraffe. So some other developments going on in Hadoop 2 is the introduction of a generic pluggable shuffle. So Hadoop Reduce is currently fixed into 3 phases. The shuffle phase, where all of the framework will fetch by HTTP all of the map outputs and then sort them, and then send the sorted results to the reducers. And this is fixed function in Hadoop 1. You can't change it. Well, but maybe you want to do other transports than HTTP, like RDMA, or maybe you want to do a clever partitioning scheme, or maybe you want to turn off sorting when it's not needed. None of that you can do now with Hadoop 1, but with Hadoop 2 and its pluggable shuffle, there are all these things that you can do to experiment. So another cutting edge. Switching gears to talk about when decisions need to be made quickly. The problem fundamentally with Hadoop and rapid or near-time decision making is MapReduce is high throughput, but that high throughput comes at a cost of high latency. You have to batch a lot of data, process all that data in parallel. This is the high throughput part. But the process of batching and the scheduling of those jobs introduces a very high latency. So you can't, it's not real-time decision making. But what we've seen is the emergence of a pattern of hybrid architectures that involve Hadoop and something from Twitter called Storm. So Storm is a distributed computation system for streaming computation. And how the meta pattern for how people are setting up these hybrid clusters is, or hybrid solutions is, so Hadoop will do batch materialization. It's the big iron. It's the crank turning over on your historical data, doing materializations or whatnot. Meanwhile, as data is streaming in, it's Storm that's processing that. and you query the Hadoop side and the Storm side together and do an in-memory join on the client to get the current up-to-date information. And Storm is also aggregating the information, and after a certain point, you have this new shard of historical data that you push to Hadoop and clear out the state in Storm and start anew. And so it's like pieces of your data are falling off Storm into Hadoop. And so the data in Hadoop is still growing. Okay, so what you get then is eventual accuracy as the Storm output is merged into Hadoop. So the architecture looks something like this. You have the front end, Linux, Apache, MySQL, PHP, right? Pushing data in real time to Storm, and user queries who want real-time information can go to Storm and get that. Otherwise, it's the traditional architecture for ingesting large amounts of data from the front end into Hadoop and or HBase for batch processing, and for the historical queries, the queries go to the Hadoop side or the HBase side. Another problem with Hadoop is the HDFS file system is optimized for streaming large files, and so somewhat limited to write once, read many use cases. Well, if you wanted to do random access over your data, if you just had HDFS, the solution space is limited, so HBase provides an alternative. You can do random indexed access, read and write on a Hadoop system, irrespective of the limitations of HDFS, which is why we see HBase increasingly used these days. But what's interesting, I think, for talking about HBase specifically is this trend of people building online analytics processing on top of HBase. So we have Urban Airship's Data Cube as an open source example. It's a Java implementation of a data cube, and I encourage you to look up the definition of data cube if you're not really sure what I'm talking about, but to summarize now quickly, it's a multi-dimensional generalization of the spreadsheet. So just think of a spreadsheet in more dimensions than just X and Y. So Urban Airship developed a data cube implementation it's pluggable, but their only backend currently is HBase with a real-time query API, so they can do slicing and dicing and roll-ups and aggregates over 10,000 events per second per node. And that was so interesting that for our next internal distribution and trend, we are packaging that. But another example is in Adobe, they're making online analytics processing, basically data cube type stuff, a service for their internal user base. So this is a SaaS service inside Adobe, produced by their infrastructure group, running on top of HBase. Offering data cube style data ingestion and processing capability for all of Adobe internally. And so I also encourage you to look at the slide deck that they produced for recent HBaseCon back in April, and also the video of that talk is online. It's very interesting. Okay, so moving on to when HQL or Apache Hive might set the wrong user expectation for Hadoop. Whoops. So the problem is that essentially SQL-like queries against data in Hadoop should return answers as quickly as competing solutions like multiprocessor parallel databases. And users who are familiar with multiprocessor parallel databases expect their selective SQL query to return something even over a very large data set quickly. But if you try to do this with Apache Hive, maybe you're a new-time Hadoop user or whatever, or you as a Hadoop deployer are now dealing with users who are trying to do this in their expectations. They submit the job, it's in queue between, 50, 100 jobs already on the cluster. It has to do a full table scan over something to produce a result, and the user's like, 5 minutes later, why isn't my job coming back? So by presenting a SQL-like language, I think Hive can set the wrong user expectations for Hadoop. Interestingly, there's a new project in incubation in Apache which promises, or threatens at least, to solve that issue. It's called Apache Drill. It's an open source clone of Google's Dremel. And if I can shorthand what Dremel is about, Google had basically the same problem. Their engineers would have to run MapReduce or MapReduce equivalent jobs to get answers from very large data stores, and they weren't satisfied to wait around for the answer either. So Google designed Dremel to do sub-second, to support sub-second results on interactive queries on extremely large data sets. And they published a paper with sufficient detail, so it looks like Apache can pick it up and implement it on top of Hadoop. So that would be awesome. And Dremel, by the way, is the engine behind BigQuery. So if you've ever used Google's BigQuery service, then you are interacting with Dremel. So the idea for Drill is it will be a Dremel clone built on top of the Hadoop platform. With the data files hosted on HDFS, MapReduce is still needed in the picture to do ETL the data to its column format. And Drill will also be able to query alternate stores like HBase. And why will Drill be faster than MapReduce? It's a completely different way of dealing with queries. So whereas Hive runs essentially MapReduce as its query language, as its query engine, in Dremel, the query is split up and pushed down over aggregation trees or iterator or execution trees, where each subset of the query is processed in parallel in a completely different model than MapReduce. Whoops. And if you squint, this strongly resembles a highly parallel search engine architecture. So Drill is in Apache incubation. It doesn't have any code yet. But yet the architecture is laid out. The roadmap is there for you. And if you wanted to make a high impact contribution in the Hadoop space, then the Drill project would be a great way to do that. So some other issues or other problems that Hadoop faces where we might find the cutting edge are issues presented by the Java virtual machine. And that is the Java virtual machine has a lot of benefits in terms of providing a sandbox and architecture and platform neutrality, sort of write once, run anywhere. But those abstractions prevent many OS and hardware level performance optimizations. So new in Hadoop 2, we see recent changes that sort of break out from the Java sandbox via the JNI, such as providing hints to the OS block cache by fadvise, or leveraging hardware checksums where the instruction sets are available. But an interesting observation is the JVM is itself open source, right? OpenJDK. So conceivably, we don't have to break out of the sandbox where the JDK is a bad match for Hadoop, where it prevents you from doing hardware and OS level optimizations. You can modify the sandbox itself. A related issue is that in practical terms, the garbage collector of Java prevents effective use of large memory systems. The larger the heap, the more severe the penalty for doing a full GC. So there have been various efforts to build in efficient second-level caches that bypass the GC domain entirely. For example, Terracotta's Big Memory, which is a commercial product, but there are open source alternatives, I believe. And also, I know that Taobao has been tinkering with OpenJDK to put in primitives for doing off-heap access or storage and retrieval of objects. So those are two, getting back to what I was saying just previously about modifying the Java sandbox to make it more suitable for Hadoop. I mean, we're already seeing some efforts in that space. Also, the new G1, which means garbage first collector, is finally workable since JDK 1.7 U4, so says Oracle. I don't know of anybody who actually runs this in production yet, but the promise of the G1 collector is that you get low in terms of tens of milliseconds garbage collection pause times with high probability, even with very large heaps. And if that actually, the promise is actually realized, then that will be excellent. That means we can finally use large heap systems in Hadoop. Whoops. Okay, so another area of interest is the issues presented to Hadoop by solid state storage. And the problem essentially is now that solid state storage is more economical and we're seeing tiered or hybrid deployments of spinning media and solid state media, HDFS has no support for that type of deployment. So HDFS can't differentiate between block storage types, so there's no opportunity for any kind of optimization. And there's no ability for layers in the stack higher, like HBase. We might want to take advantage of that. We can't because there's no API for it. But if we did have that support, then we could consider interesting ideas such as adaptive differentiated block placement for HBase data files. Consider a column family that is mainly seeing random read access, and it's on spinning media, and it's seeing a lot of random read access. Well, maybe we can migrate those blocks to solid state storage so that we can support much higher random read IOPS over that data. If we had that ability in HDFS to differentiate and migrate those blocks, then we could keep statistics on column families and do that type of migration and see what type of benefit that might be. So there are two JIRAs open. There's HDFS 2832 and HBase 6572 that are exploring these ideas, and it's still very early. And so if you wanted to get on a cutting edge of Hadoop, then participating in those issues specifically would be a way to do it. But more generally, SSDs will the low latency access to data in an SSD will expose bottlenecks in the stack, because all of our software in Hadoop has been optimized or has been running in the regime of spinning media. So I'm sure that we have issues with locking and overly enthusiastic use of threading and data structures that may not be optimal, and internal contention points in the JVM. And none of these issues have been a problem now because we've been dealing with spinning media. But when we move to solid state devices and we want to try to support those high IOPS, we'll have to knock those issues down. And Dhruba Borthakar at Facebook has actually done some experimentations in this space and has identified several issues. So there's definitely room for improvement and an opportunity to improve the Hadoop and HBase stack substantially for SSDs in this area. And finally, an area of cutting edge or emerging interest is GPU offload, and we really haven't considered this for Hadoop at all. So offload of parallel vector math to GPU is, in academia at least, and in scientific computing circles, you see anywhere from 30 times to 3,000 times improvement in running times of parallel algorithms by using the GPU's vector engine as an accelerant. This hasn't been considered yet in the Hadoop context. An interesting open source project that I saw recently is so-called root beer compiler. This thing can convert Java bytecode into a native GPU application or execute it on the hardware if a GPU is not available. And it does it in a way that's different from any previous open system that I know of, in that you don't need to express your data structures as primitives only. You can actually use objects and object graphs, and root beer will create on GPU structures that reflect those Java structures automatically for you, which is really interesting. So maybe we can consider some sort of integration of root beer into the Hadoop as a new type of mapper task or a new type of reducer task that makes this type of acceleration easily accessible to people who are writing MapReduce jobs. Just an idea, it's not been done at all. So to summarize, and maybe to leave you with a few predictions. So although big data, we might consider big data to be a marketing term, the underlying phenomenon is not. And as you saw in the beginning of my presentation, the potential scale of this space is enormous, and it's not going away. And so Hadoop is and will be a widely used commodity operating system for big data for at least the next 3 to 5 years. And the Hadoop ecosystem will continue a rapid pace of evolution. But I think if you're familiar with Gartner's hype cycle, the Hadoop system is not going to escape the trough of disillusionment. And I think that we're not at the trough of disillusionment yet, that we're still heading towards the peak of inflated expectations about what Hadoop can do. And so there will be that drop-off. But beyond that is when people will be serious and sober in understanding what Hadoop's benefits are as well as its limitations. Vendors in the Hadoop space will have to differentiate, which means there'll be diversity in the ecosystem, but with some fragmentation. I think that Hortonworks and Cloudera and MapR and other vendors in this space will aggressively compete and pull apart and cause some fragmentation, and I think that's inevitable. And so it's an open question whether the open core will maintain its coherency. But although there's that risk, the benefit is because they're pursuing all these different directions, there'll be a lot of diverse ideas in the ecosystem. So in the short term, over the next 1 or 2 years, I expect to see that HDFS and HBase will see closer co-development, especially regarding solid-state storage. Apache Yarn will graduate and become its own top-level project and maybe become an ecosystem which goes beyond its Hadoop roots entirely into the larger grid computing space, because it's so general. It builds on Hadoop, but it's not Hadoop. It can be so much more, right? I think Apache Giraffe will continue to grow and do well as a new project, and I expect that Apache Drill will be realized, and so we'll have this new high-performance query engine running on top of Hadoop that you can leverage. So that's the end of my presentation, and for the remainder of my time, if there's any, I'm open for questions. How much time do I have left? Did I run out of time? Huh? 10 minutes. Okay, so I can take questions for 10 minutes, or if you don't have any, then it's a short break, I guess.
Oh, I'm a student. I have a question. What's the difference between MPI and Hadoop?
The difference between MPI and Hadoop?
Yeah.
Well, the correct question is what's the difference between MPI and MapReduce? And they are two frameworks for doing distributed computation.
They are also clustered.
They are both clustered
yeah.
compute solutions. I would say that at a high level, the difference between MapReduce and MPI, for me, like the main reason why they would be different is MapReduce has fault tolerance built into its model, such that if one of your workers dies, then its computation will be restarted automatically by the framework, and you don't have to worry about that. Whereas MPI, if one worker dies, you have to restart the entire computation. So that could be a negative. On the flip side, MPI is extremely general purpose message passing framework, and so you can get really high efficiencies in what you implement there that you wouldn't be able to get in MapReduce, because MapReduce comes with its limitations, right? Like with MapReduce, you have to do MapReduce. With MPI, you can do practically any kind of parallel algorithm, with the caveat that if one worker dies, you have to restart. Okay.
Hello. Real-time Hadoop. Any comment on that? And Hadoop as a service, is that possible?
So the question is, are the following two things possible? Real-time Hadoop and Hadoop as a service. Okay. So let's talk about them separately. Real-time Hadoop is possible if you redefine what is real-time. I mean, what is Hadoop? So MapReduce. MapReduce is a batch computation. So from start to finish, you have to wait for the answer. That's obviously not real-time. But if you devised a MapReduce, say running in Yarn, for example, that is continuously running and accepting new input, and you get output as soon as it's available, then this would be a real-time MapReduce, right? So I think it's more of a marketing question than a technology question, how you define the real-time term. So in that sense, it's possible. But is MapReduce itself going to be suitable for real-time ever? No, it's just not. It's design space. Now, Hadoop as a service, I think Hadoop 1 as a platform is not suitable for multi-tenancy. But Hadoop 2, we're starting to move in the direction where it is, right? With HDFS, first of all, we've integrated security up and down the stack now for Hadoop 2. HDFS allows you to partition your namespace. You can have multiple name nodes, the federation feature that I was talking about. So you share the single pool of data nodes for economy of scale, but each customer has its own private namespace, its own name node that you can provision. So that's definitely pure multi-tenancy there. And with Yarn, each job that's executed is its own separate cluster, which is also highly multi-tenant, as all the resources for one job doesn't interfere with the resources of any other job. So it's certainly technologically feasible for you to deploy Hadoop 2 and build automation on top of that to make Hadoop a service for some pool of customers. Yes, definitely.
Hello. I have one question about the core processor in HBase. What's your did you recognize the end user programmer to use core processor feature to write his program on the HBase platform? Thank you.
Okay, let me restate that back to you to make sure I understood your question. Did we design the coprocessor feature of HBase to be suitable for end users? Was that the question? Yes. The answer is no. Coprocessors, as currently engineered, loads the code into the address space of the region server. It becomes one with the region server. And there's no fault isolation or CPU limit or heap limit. There can't be. It's just a jar loaded into the Hadoop. It's kind of like OSGI, right? You just load a module, and now it's running as part of your application. And we do a little bit of namespace isolation with class loaders, but no, you don't want arbitrary user code running in your region server. It's a tool for system integrators. You're deploying an HBase platform. You want to provide your users with secondary indexes, with transactional support, with some custom feature. You, as the system integrator, build that in and deploy that as a coprocessor, and it becomes part of your solution. Now, longer term, we do have JIRAs open for so-called external coprocessor. At that point, I think it's feasible to run user code arbitrarily. And the difference between an external coprocessor and the currently is that external coprocessor will be loaded in a separate process, independent from the region server. It'll be an umbilical protocol that over a local socket or whatever, where the region server talks to the coprocessor in the external process and vice versa, right? But that will be fault tolerant in that if that external process ever dies, the region server will continue. And since it's a separate process, obviously the code running in that process can't interfere with the internal state of the region server. And furthermore, you can use things like C groups to limit the resources of that process and kill it if it uses too much CPU, if it uses too much memory, for example. And at that point, yes, you could use it for hosting user code, but not until then. And yeah, I guess I was remiss in not mentioning that in my presentation, because that's certainly a cutting edge of at least HBase specifically, because that external coprocessor has not been implemented yet.
There are many people in Taiwan know about the Apache Foundation and use many projects from this foundation. But many people are user role. Less people contribute the code back to the Apache. So as the committer in HBase project, do you have any recommendation for us?
So the question is, if you would like to, you're feeling guilty about not contributing code back, and you'd like to, how would you go about doing that?
Very interested. I am very interested for this, getting involved in Apache.
Yeah, okay. Yeah. So, well, each project in Apache typically has a wiki, and on their wiki they have a page, how to contribute. And so if you, for example, if you're interested in contributing something to HBase, have you ever looked at our how to contribute wiki page? That would be the place to start, right? Because we spell out the, if you wanted to contribute something to us, this is our expectations for you. And if you follow those guidelines and then interact with us on the mailing list, like just drop us an email. Hi, I'm sorry I didn't catch your name, but hi, I'm you from Taiwan, and I have this really great feature that I would like to contribute. How do I go about doing that? I mean, we'd interact with you on the mailing list, so definitely email the mailing list, right? We can guide you. Or you can open a JIRA in the Apache tracking system and attach your proposal as a patch and generate. That's the usual way once we're talking about code and design specifics, how we as a community interact with each other. So you would just be another member of our community interacting with us in that way. So anyway, the first step is to look at the project's how to contribute page so you get an idea of how you need to interact with the project. But if you don't have anything to contribute necessarily and you just want to start interacting with us, then introduce yourself on the mailing list.
Yeah, I also represent from the Trend Michael. Trend Michael now we are probably the #1 in terms of the Hadoop contribution with the help from the Andrew. We are #1 in, especially in the Asia. In the worldwide, we are probably #7. So, and also we have a second group now is a cost stack. We also have some committer in the committee already. So if anyone want to have more join, we have more talk involved with the contribution, you can contact with me. My name is Oscar, I found Trey Michael, or you can talk to with the organizer. 就是说你可以找那个我们那个主办单位会给你们那个单子。那我想趋势这边我们愿意搬多在这边，我们会跟大家一起合作。哦，就是除了 Andrew 刚才讲的 Hadoop 这边，我们还有一些 Cost Stack 这边，我们现在是 Committer， 好不好 ？I just speak a little Chinese.
It's okay. I've been in Taiwan for a long time, and I understand. It's totally okay. Sometimes I pick up a little bit of what you're saying, and so I'll be in a room full of engineers, and they'll be speaking in Mandarin. But the technical terms are universal, right? So they'll talk about whether a linked list is better than a queue or something like this. And I'll say, no, you want to use a queue for that. And they'll be like, shocked, like, you understood what we said? Not really. But that's a great point. And actually, Trend has engineers who are passionate about open source. And I know that they have, in the past, organized things like Apache Big Hackathons. So if there's some way for you to find out about those, just come over and visit, and you'll be able to interact with Trend engineers who are passionate about open source and can guide you, definitely. Okay, well, if no more questions, then I thank you for your time.
Thanks, Andrew Purtell, for his presentation. 谢谢 Andrew Purtell 精彩的演说。